Good morning, students. In this chapter, we will study about Laplace transform. The contents of this chapter is first we define Laplace transform, and we'll talk about region of convergence for Laplace transform, inverse Laplace transform, properties of Laplace transform, and analysis of linear time invariant systems using Laplace transform. Linear time invariant systems characterized by differential equation analysis of systems, LTI systems characterized by linear constant coefficient differential equation, system functions, and block diagram representations. This is the outline. Now, as you know, in chapter 4, we studied about continuous time Fourier transform. And continuous time Fourier transform enables us to do a lot of things. For example, we can be able to find the frequency response of linear time invariant systems. So that means we can change from h of t to h j omega. We can be able to study signals in general in frequency domain. So we change from time domain to frequency domain using Fourier transform. And we can study the signals in frequency domain. We can be able to solve different systems described by differential equations in frequency domain, and we can change to time domain from frequency to time domain. After we analyze in frequency domain, we can go back to time domain, and we saw how we can analyze modulation, for example, modulation of signals using frequency domain, and also we studied so many examples. Now, why do we need another transform? That means why do we want to study Laplace transform? So in a way, one way to view Laplace transform is it is just an extension of Fourier transform. It is used to analyze a more broader class of signals. For example, signals having infinite energy. That means the integration from minus infinity to infinity x of t dt is equal to infinity, or the energy, for the case of the energy, x of t, the whole square dt is equal to infinity. If we assume this is a system, if it is infinity, then the system is unstable, as we studied in chapter 2. Now, in many applications, we do need to deal with unstable systems. So, for example, how we can be able to stabilize systems. For example, how we can be able to stabilize an airplane flying at a certain speed, a space shuttle flying at a certain speed, and some other systems, for example, oscillators and so on, in electrical engineering, oscillators. So how do we analyze such systems? Such systems can be analyzed using Laplace transform, very important tool. So the Laplace transform of a system, if I have h of t here, it is from minus infinity to infinity, h of t e to the power of s t dt. And S is a complex number. S is sigma plus j omega. And sigma is the real part of S, and omega is the imaginary part of S. If we have sigma is equal to 0, we are coming to the Fourier transform, because S will be j omega, and if we substitute here, we have h of j omega from minus infinity to infinity, h of t e raised to j omega t dt. We saw this in the previous chapter also. So h of s in general, we call it the eigenvalue. So in Laplace, in the Laplace case, we call it the Laplace transform of h of t. That's going from time domain for the system h of t, from time domain to the Laplace domain h of s. Now, let's define formally the Laplace transform. The Laplace transform of a signal x of t. So we are going to Laplace, then we have x of s is from minus infinity to infinity x of t e to the power of st dt. This is called the Laplace transform of x of t. This definition is not enough. We need to have also what we call the region of convergence. The region of convergence means the set of S. The set of S. Remember, the S plane it is a plane where we have the real part in the x-axis and the imaginary part in the omega axis. It is a region where x of S is convergent, or the Laplace transform exists. So formally we define the region of convergence is the set which consists of S is equal to sigma plus j omega, such that the integration from minus infinity to infinity x of t e to the power of sigma t dt less than infinity. Why do we have this? Because here, if we substitute S is equal to sigma plus j omega, we have x of t multiplied by e to the power of sigma t times e to the power of j omega t dt. So if we see this equation, the Laplace transform is nothing but it is the Fourier transform of the signal x of t multiplied by e to the power of sigma t. And the Fourier transform, we know that it exists if the integration of the absolute value of this x of t e to the power of sigma t dt is less than infinity, or the energy of this product function, the product of x of t times e to the power of sigma t is less than infinity. So that's how the region of convergence comes. It is a set S such that S is equal to sigma plus j omega, where the integration from minus infinity to infinity x of t times e raised to sigma t dt is less than infinity. We call this the region of convergence. Of course, if sigma is equal to 0, that means it is a j omega axis, and we have the Fourier transform of the signal. Now let's see here, for example, x of t e to the power of at ut. This is what kind of signal is this? This is a right-sided signal. If a is less than 0, what kind of signal we have? We have a growing exponential signal. So if we assume this is a system, that means the system will be an unstable system, and the Fourier transform does not exist. However, the Laplace transform exists provided we have a certain region of convergence. If a greater than 0, as you know, it is a decaying exponential signal, because this is a right-sided signal. Why it is a right-sided signal? Because of the unit step function. So it is a decaying exponential signal. And if it is a system, for example, if it is h of t, the impulse response of a system, the system will be a stable system. Now let's find the Fourier transform of x of s. The Fourier transform of the Laplace transform of x of t. It is from minus infinity to infinity x of t e to the power of st dt, from minus infinity to infinity e to the power of at ut e to the power of st dt. And because of unit step, we start the integration from 0 to infinity. Then we combine a and s. We have e to the power of s plus at dt. Now what will be this value? This value will be convergent depending on s. Let's go to the class notes here. The class notes here. S, as we know, is sigma plus j omega. Let's substitute sigma plus j omega here. Then we have negative 1 over s plus a, and this is from infinity to 0. So we have infinity here, and e to the power of 0 is 1. We have 1. But if I substitute s here, sigma plus j omega, I will have e to the power of sigma plus a times infinity, e to the power of minus j omega times infinity. This part cannot be greater than 1 because I have j here. So this is the important part. So this part will be finite if sigma plus a greater than 0. If sigma plus a greater than 0, at infinity it will be e to the power of negative infinity, which is equal to 0. And the Laplace transform will exist. It will be convergent. If sigma plus a is less than 0, this will be e to the power of positive infinity, because sigma plus a is negative, this is negative positive, so e to the power of positive infinity is infinity. Then the Laplace transform does not converge, so does not exist. So the Laplace transform of x of t e to the power at ut, which is the right side of signal here, will become x of s 1 over s plus a if sigma is greater than minus a, or real of s greater than minus a. Remember, real of s is in the x-axis, so sigma is equal to minus a means the vertical line. So to the right of that vertical line, x of s will be convergent, or it exists, and it will become 1 over s plus a. Let's have another example here. Left-sided signal, x of t minus e to the power minus at u minus t. Why it is left-sided? Because of u minus t. So it is the flip of ut. U minus t will be equal to 1 for t less than 0, is equal to 0 for t greater than 0. Now if a greater than 0, that means a positive, minus a is negative, but t is negative because we are going to the left, then this will be positive, minus 80 will be positive. So it's a growing exponential signal. The Fourier transform does not exist. If a is less than 0, minus 80 will be negative. So minus a, it is a decaying exponential signal. Okay, a decaying exponential signal. Then the Fourier transform exists. Now let's calculate the Laplace from minus infinity to infinity, x of t e to the power of minus st dt. Substitute again e to the power of minus at, then combine these two, s plus a. The interval of integration will become from minus infinity to 0. Why? Because of u minus t. So this will be 1 over s plus a, e to the power of s plus a times t, from 0 to negative infinity. So e to the power of 0, e to the power of 0 is 1, and this is infinity. Minus infinity times minus here, it will become positive infinity. And again, this term will be convergent depending on this. X of s will be convergent depending on this e to the power of s plus a times infinity. So substitute as sigma plus a j omega times infinity, and this will be e to the power of sigma plus a times infinity here. This part is maximum, it can be 1 only, but this part, depending on sigma plus a, it will be either convergent or not converging. So if sigma plus a greater than 0, this will be e to the power of positive infinity, it will be infinity, and it will not be convergent. If sigma plus a less than 0, this will be e to the power of negative infinity, which is equal to 0. Then x of s is 1 over s plus a, 1 minus 0, which is equal to 1 over s plus a. So the Laplace transform will exist if sigma plus a less than 0, or real of s is less than minus a. So if we go to the slides again here, now we have this right-sided and the left-sided signal. The right-sided signal, e to the power of at ut, right-sided. Laplace transform, 1 over s plus a. Real of s greater than minus a. You see, this is the real axis, which is sigma. The vertical one, the imaginary axis, j omega. So it will be convergent for sigma greater than minus a. Left-sided signal, the same, 1 over s plus a. it will be convergent if real of s sigma less than minus a. So what is the difference between the two? Only the region of convergence. One of them greater than minus a, the other is less than minus a. Okay. Now, what about at s is equal to minus a? At s is equal to minus a, this will be 1 over 0. 1 over 0 is infinity. It is not convergent. So that's why it's a broken line. And s equal to minus a is called the pole of x of s. The pole means the location where x of s is infinite. And at s equal to infinity, we have 1 over infinity is equal to 0. Then x of s is 0. So s equal to infinity is the 0 of x of s. S is equal to minus a is the pole of x of s. So in general, x of s is a rational function with a numerator n of s and denominator polynomial d of s. The roots of the numerator polynomial n of s will give me the zeros of x of s, and the roots of the denominator polynomial d of s will give me the poles of x of s. Now let's do some examples here. Let's say we have here x of t e to the 3 times e to the power of 2t ut minus 2 e to the power of minus t ut. Both signals are right-sided signal. Okay, let's do the Laplace transform of these two. So it is from infinity to minus infinity. Then we have from 0 to infinity. The first case, e to the power of 2t times e to the power of minus act. We can combine this e to the power of minus s minus 2t dt. The second one, e to the power of s plus 1t dt. Now, this one will be convergent if we substitute s is equal to sigma plus j omega. It will be convergent if sigma minus 2 is greater than 0. If sigma minus 2 is greater than 0, means this is positive, then it will become e to the power of negative infinity. E to the power of negative infinity is 0. 0 minus 1 is minus 1. So I will have 3 over s minus 2. And this one will be convergent if sigma plus 1 is greater than 0. So in that case, this part will be e to the power of negative infinity, which is 0. 0 minus 1. And again, this will be 2 over s plus 1. So the first part will be convergent for sigma minus 2 greater than 0. The second part for sigma plus 1 greater than 0. That means we are having in the S plane sigma greater than 2, one region sigma greater than 2, the second region sigma greater than minus 1. So we need to take the common for both. The common means the intersection between the two regions, sigma greater than 2 and sigma greater than negative 1. Of course, since 2 is greater than negative 1, the common will be sigma greater than 2. So the overall signal x of t will have x of s is equal to 3 over s minus 2 minus 2 over s plus 1 if sigma greater than 2. And again, this one we will combine them, the denominator together. The numerator, after simplification, after we combine these two, the numerator will become s plus 7. The denominator, s minus 2 times s plus 1. Now, and the region of convergence, the overall region of convergence, the common for 2 is sigma greater than 2. Now, n of s is s plus 7. So s is equal to minus 7 is the 0. T of s is s minus 2 times s plus 1, which is when we make this is equal to 0, we will have s is equal to 2 or s is equal to -1. So the zeros are s is equal to -7 and infinity at infinity, because this is the degree of the denominator is 2, the degree of the numerator is 1. So we will have 1, 0 at s is equal to infinity. And the poles is s is equal to 2 and s is equal to -1. In general, the number of poles is equal to the number of zeros. So when we draw the region of convergence, first we put the poles. The pole is at -1 here, and another one with a cross sign, another pole at 2 here with a cross sign, and the zero we put a circle here at -7, and the other 0 is at infinity. So of course we will not mark it because it's at infinity. So this is the real axis sigma and the imaginary axis j omega. So this is the region of convergence greater than 2. Okay, so we have another example here. 3 times e to the power of minus 2t ut, 2 times e to the power of minus t ut. Again, this one, the Laplace transform is from minus infinity to infinity x of t e to the power of minus st dt. Then we have here e to the power of minus st is common. It comes inside here. So we have e to the power of minus 2t times e to the power of minus st. Then we integrate from 0 to infinity because of unit step. Both are right-sided, by the way. Then we have e to the power of minus s plus 2t dt. And when we combine this and this, we have e to the power of s plus 1 t dt. So we have these two. Now the first one will converge when if sigma plus 2 is greater than 0. That means real of s greater than -2, then the Laplace transform is 1 over s plus 2. The second one will converge if sigma plus 1 is greater than 0 or sigma greater than -1. In that case, it will be 1 over s plus 1. So the first part is times 3. We have here 3 over s plus 2 if real of s greater than -2. And the other is minus, here I have -2 over s plus 1 if real of s greater than -1. So what is common for the two? Real of s greater than -2, real of s greater than -1. The intersection between these two sets, or the common region, is real of s greater than -1, because -1 is greater than -2. So the overall region of convergence is real of s greater than -1. Then we simplify this. When we simplify, we have here s minus 1, s squared plus 3s plus 2. So what are the poles? The pole are s is equal to -2 and s is equal to -1. The zeros, s is equal to 1, and at infinity we will have another 0 because the denominator is degree 2 and the numerator is degree 1. So the denominator is greater than the degree of the denominator is greater than the degree of the numerator by 1. So we will have 1, 0 at infinity. So again, this is the plot of the region of convergence. So this is how we plot. First, we mark the poles. Pole at -1, cross sign. Pole at -2, 0 at 1. And the region of convergence is greater than -1. And we have broken line at -1 because s is equal to -1 is the pole and it is not convergent at the pole. That's why. So this is the S-plane representation of the Laplace transform of x of t, which is this one. So note that there are poles and zeros at infinity. If the order of the denominator polynomial is greater than the order of the numerator polynomial, then x of s will become 0 as s approaches infinity. If the order of the numerator polynomial is greater than the order of the denominator polynomial, then x of s becomes infinity as s approaches infinity. For example, here we have 1, 0 at infinity because the order of the denominator is greater than the order of the numerator by 1. In general, if the order of the denominator polynomial is greater than the order of the numerator polynomial by k, there will be k zeros at infinity. If the order of the denominator polynomial is less than the order of the numerator polynomial by k, there will be k poles at infinity. Okay, with this we finish the first part of the lecture for the Laplace transform. See you in the next lecture. Thank you for listening.